All right. Well, hello, everyone. And thank you to Aaron and Gabriel for setting this up and everyone for being here. And I want to talk a little bit about some sort of philosophical almost take on illustration, or sort of one approach to thinking about it. And that is to think about the idea of taking abstractions and playing around with them in physical spaces and physical reality, if you will. And we sort of do this whenever we do mathematical modeling, but this is but we can want to do the sort of reverse. So instead of thinking about having some sort of physical idea and then seeing what that means in the abstract, what happens if we take abstract ideas and try and understand them by looking at physical models? So instead of having the abstract model tell us something about the physical, we want the physical to help us think about and tell us something about the abstract. And to do that, we want to sort of build really clean bridges between abstraction and physical things. And so this is a good place to start, I think, with that, because so this is a laser etching a Mandelbrot set, but and the laser is set up with a bitmap, and I've created the bitmap so that it's the same resolution as the firing of the laser. And so if you think about it, the bitmap is generated by running an algorithm on a given point and saying, is that point in or out of the Mandelbrot set? And so what you have here is the laser, as it goes past, running through a proxy, running the algorithm, and then choosing to fire or not on each given point. And so you're getting this very precise and clean relationship between the mathematics on the one hand going into the physical object. And this piece of mylar that was cut here was then used as a stencil to create this. This is part of the Mathamalchemy exhibit, and I encourage everyone to look that up if you haven't come across it. It's a wonderful collection of mathematics and play and storytelling. So that's a sort of taster, and this image was so lovely, wonderfully set up or in one of the initial talks, which is to look at things, starting like imagery is the first place we can really think about that relationship between physical sort of visual things on one hand and mathematics on the other, and we can start to show things. And this is these rational geodesics, but they're going through all the points are just the solutions to all quadratic polynomials. They're sized by the discriminant. You got some lovely detail in the last talk on that. And so you can show this image to someone and they will immediately start seeing that there's something there. But you can also, if you're used to certain sorts of images, you might look at this and see, for example, geodesics on the upper half plane, which are definitely there, and also sort of grid patterns in perspective, and those are also there. And so we can look at this just as the plot of quadratics, and then think about the structures that we're seeing. And then you can actually find those structures in the process. And the nice thing is you can actually find both of those objects that I've just described in how you solve polynomials. And there's a very nice way of solving quadratics that I'm going to go over fast. So if you follow, great, and if you don't worry about it. But look at the paper. But you start off with the lattice in the coefficient space. That's a three-dimensional lattice. You've got ax squared plus bx plus c is equal to 0. And then so I then can projectivize that, because if I multiply all the three coefficients by a constant, I get the same roots. And so I can look at all the points which have complex roots, and they sort of form a cone in this three-dimensional space. When I projectivize down, I get a disk. If I regard that disk as the Klein model of hyperbolic geometry, and so and that has the straight lines in the lattice become straight lines in that. And then you convert that Klein model into the upper half plane model, and you've just solved your quadratic polynomials. And so the lines you're seeing here are lines in coefficient space of a lattice. They're not in the same order, but there is something, you're really seeing lines of the coefficients. So if you can do this for quadratics, and then you can sort of study it and have good mathematical research questions, or find mathematical structure from the image. Incidentally, I have the names. All the work I'm showing today is intensely collaborative. It's always with other people, and the names hopefully will be on most of the slides. And so if you can do the quadratics, you can then say, well, what about the cubics? And here are all cubic polynomials. And there's an important point here, especially when moving from the quadratics to the cubics. This is a very mathematical image, but it's also somewhat an artistic one. There's questions of aesthetics and taste in my choice of colors and exactly the scaling on size, trying to produce the best image, things which are not, you're setting up some way of how you're going to visualize mathematical information, but you're not, the ways you can do that, you have to make sort of choices, and there's taste and sort of aspects. So, you might like or dislike this image, but that's not just the pure mathematics. That's whether or not you like the choices I made in trying to pick. So one thing you can quickly see when looking at this image is that the cubics really don't like the quadratics. So hopefully it's sort of coming across as I flick between the two, but you can see it, focus on any dot in this, you'll find a gap turning up in this. So we can immediately start to see, again, mathematical structure. And if we zoom in to the details of it, we can see here, right, all sorts of really interesting structure. And they're sort of spiraling into points and various things. This is not a completely disordered image, but it's also not got the sort of clarity of order that you saw in the quadratics. There's a lot going on, and it's really interesting that the cubics almost make a Jackson Pollock style image when you plot them. And I think if you showed someone this, they wouldn't necessarily expect it immediately to be quite a simple mathematical procedure to create this image. And I think, from this image, there's probably mathematical ideas that we don't even really have the right conjectures to ask about yet. So I think there's sort of interesting mathematics that we can see in here. And as researchers, we can look at this and have questions. And I think this is an important part of, as we build these bridges, we get the ability to understand abstraction by looking at it not within the world of abstraction, but in worlds where we can translate into that. And that gives us the opportunity to push research forward. Mathematical imagery and art is often thought about in terms of outreach or pedagogy, but images like this can also be huge drivers for a research agenda. And so I think in that idea, what I want to do now is to go on to talk to some examples about just simply thinking about how we build those clean bridges between abstraction and the physical world. And so I think this is a good example to start. This is a 3-axis CNC, and you can see it has a rail there, and then the rail is on a gantry, and then on the rail we have a thing that can move up and down. And so this is literally controlled by 3 numbers. I can have my position on the rail, my position of the gantry, and then the height of the tool. And so what you're seeing here is a physical version of a vector space with a basis. The X, Y, and Z 3 numbers are being explicitly translated into a physical form. And of course, once we've got a vector space, there's all sorts of things you can do within a vector space. And so, of course, you can connect points in a vector space up to create curves, and then you can sort of ask what happens when you start moving a tool along those curves, and then you can put material in the way, and suddenly you've got this sort of manufacturing setup, and you've got something which has a very clean mathematical description, and you can now start to sort of think about how you're going to make objects using that sort of setup. So here you have a drawn illustration of a human, and it is cutting round to get that. So we're not really seeing mathematics here, but we're using the mathematical bridge to sort of think about a drawing, pull a drawing into the world of abstraction, and then pull that out into something we can cut. And so here you're going back to a more traditional modeling effect. You're starting with the image of a human you want to make. You're pulling that into abstraction in the form of curves, and then you're pulling those curves out through this bridge we have in the CNC. And we hope that the physical object we had to start with is going to be like the physical object that the machine makes. So in other words, there's some sort of genuine work happening as you go through the path through abstraction. And what we want to do is sort of take that and say, well, what happens if instead of starting in physical reality, moving into abstraction, moving back, we start in abstraction and just move out. And we can also step up to a more complicated sort of machine. So this machine has 3 linear motions to it. There is one. Here's another. And there's actually 2 going together. But in addition to that, you've got a bit more control because you also have 2 rotary actions happening. So hopefully they will happen. There we go. So I can rotate this piece in around. This is rotating around. It's actually the y-axis is the vertical in this. And then this is rotating around the x-axis. And so with those 2 rotations, I'm now not just controlling a point, I'm actually controlling a point in the tangent bundle, if you like, a point in a direction at every, for the machine. And that can affect how my tool interacts with the material. And so here is an example of the machine running. So you can, by changing the direction, so we did some roughing where we just did the rotary, and now we're rotating, and the tool is staying always at right angles, always normal to the surface. And so we're able to not just produce curves, but we can actually mill out the surface of a sphere here. And then you can have some fun cutting into the sphere and taking advantage of the fact that the sphere, if you cut a cylinder into a sphere, it's going to, cylinders intersecting into a sphere are going to intersect themselves, so you can sort of build structures that have interesting internal behavior. So you'll see that in a second as we sort of, these cylinders start to intersect, we start to have a sort of outside frame, and then there's a dodecahedron in the middle that's being formed. So now let's take this machine and think about how we use it to create not just sort of, a sphere is not, a sphere is a lovely mathematical object, but it's not a mathematical object we need to sort of hold to understand, or we have plenty of other ways of holding and thinking about spheres. So let's think about doing a different surface. And so here we are milling onto a little bit of the Bath sextic, which is a solution of a degree 6 polynomial in X, Y, and Z that has some nice properties. And so we're using, again, that ability to have the tool always at right angles to the surface. That allows us to do a lot more efficient cutting of a surface. And that's part of the, there's an interesting sort of corollary you get when you start to think about the abstraction and the physical thing working well together. You often end up finding interesting ways to make manufacturing more efficient because you're thinking about how you can think about that abstractly. And so, for example, you can get a smooth surface more efficiently with an idea like this, where you're staying on the normal, and so you can cut with a flat end mill. And here is the finished piece. And so the piece you saw being milled, there are a total of 20 of those in this piece, one for each vertex of the dodecahedron. And then you put brass rods in to get the whole of the surface. And if you really want to think about the surface, you imagine the wood continuing in. When you have the brass rod, you sort of put a bit of brass around where the surface is, and the surface sort of dives in and hits a point in the middle of the rods. And at least the idea is the rods are a fixed length. And when you have it, you dig the holes so that when the rod is sort of fully in, the two pieces are the right distance apart. Theoretically, that's completely true. In practice, I was cutting the rods by hand, so they're not a consistent length. So the final piece doesn't quite have that precision. But as a mathematician, I feel it's enough. The idea is often enough for mathematicians. Engineers prefer to have ideas actually working in reality. So let's think about how we might make a surface like this. So we've got the notion of an algebraic surface, and we want to pull that out and have a physical model we can hold. And so one way we might do this is use the algebraic surface to make a 3D mesh, and then we can 3D print that. This sounds like a simple process, and anyone who's actually done these sorts of things, you find that you have to learn any machine. I'm sure Bathsheba can tell you plenty of war stories on trying to go from the perfect mesh into actual physical things. But this is one path. But there's a sort of intermediary stage here. You've got the algebraic surface generates a model, and then it's the model that you print. Can we make that cleaner? Well, in fact, there's an additional step that's going to happen because the 3D mesh can't be printed. That's not something the machine, the 3D printer has no understanding of that. It has a point that I can move around, for example. So one of the ways you can do it is to take your 3D mesh, take another step away from your original algebraic surface, to slice that path, and then you give a path for the machine to follow. So a different approach would be to say, well, let's go straight from the surface to paths on the surface with the information about the normal to the surface at every point. And then, so now we can stay on the abstract surface and generate how the machine is going to move. And it's a sort of interesting, like, dimension, thinking about dimensions is quite fun here, because often we want to make surfaces, which are naturally two-dimensional objects, but the machine is basically moving a point with time, so that's naturally a one-dimensional process. So we've somehow got to get our two-dimensional thing down to a one-dimensional thing. And here the one-dimensional thing is sort of these paths on the surface with normal. And then we can just put those into the machine and cut them. You know, again, there's a sort of simple idea. I mean, you start to hit, you know, reality resists abstraction being pushed into it, I feel. And so you often have to, you know, you have to gentle the abstraction in. And so in this case, as you saw with that sphere cutting, we first had to cut roughly close to where we wanted to be before we went in and made the finish path. So we might use a different technique to get close to where we want to be. And often that's easiest to do using meshes and so on. Get close to where you want to be and then run your special path into that setting. And it's worth noting that there could be ways that we take these paths on the surface with normal and get them into the 3D print. But the idea is that we've sort of made something that is a lot closer to the abstract object. We've tried to minimize the number of steps we go through to what is necessary to translate from abstraction into the abstractions of a machine. As I said, there's that a machine can't do two-dimensional things, or this, I guess there are some machines that can, like a wire cutter that moves a wire, so it's moving a line through space. That is actually naturally cutting a two-dimensional object. But many machines can only do a one-dimensional thing. So that changing from the surface into one dimension, that is something you just have to do because the abstraction of the machine requires that sort of change. But we're trying to basically reduce to the only the necessary ideas. And so here is another lovely and impressive machine. This is a plasma cutter, and it's sort of basically harnessing a little piece of the surface of the sun in order to cut pretty shapes out of metal. And here, you know, the model for it is actually even simpler because this is really a 2D cutter. You can see that the head goes up and down, but actually that's to sort of basically clear it from the material. When it's cutting, it needs to be a fixed distance away from the material. Now, as metal bends when it's heated, that distance can actually change as it's cutting, and these machines are quite clever. They know from the voltage jump created by that plasma how far apart they are, and so they will ride the surface as the metal sheet bends. So you're doing 2D cutting, but you're doing 2D cutting onto a surface that changes as you cut it. So luckily you don't have to think, you have to think about that in the manufacturing side, but when you're designing the path, you just draw a two-dimensional path and you offset a little bit so you can get precise pieces. And the nice thing about these machines is you can cut large pieces of metal. So here is an example of something made on, the final thing was not made on the machine you just saw, but all the prototypes were. And so the question, you know, now you've got one level of abstraction, I can draw shapes and I can make metal versions of those shapes. I'm now in the abstract world, so I can ask, well, what shapes do I want to cut? What do I want to do with shapes that I know that I can put into an abstract space? And I know that the metal that comes out will have some respect for that abstract shape. And so you can now start to layer on more mathematical ideas. So here is that sculpture. It got its bottom cut off, and it's being installed at the University of Arkansas. But the nice thing is we've got this abstract model. We can now do other things with it. So our method of sort of creating interesting shapes is used here. Instead of making a sphere, we're going to make a sort of hyperboloid shape. And so let's now look at what it is we're doing to create the shape. So the idea is we're wanting to create T-shaped beams, but that curve. And if you take pieces of metal, they sort of don't really mind bending in this direction, or you know, sort of bending, but what they don't like to do is twist. So if you've got a piece of metal, you can sort of locally bend it in different ways to create a curved path without actually changing the geometry of the surface. And so here now you could basically have the idea that you can have a frame and you can bend one piece onto the other, and that top piece that's bending stays as a developable surface. It stays at something as flat as it bends round, because we're avoiding that twisting. So when you have that sort of torsion, that twisting, that changes the geometry. And so that's something that a strip of paper or a strip of metal can't do without having to sort of stretch internally. And it turns out that there's some really nice differential geometry that goes into how these things move along a curve. So here we have the sort of classic way to put a frame, so that little thing that's moving along with its three directions, that's a frame, and we put it at every point along this curve. And the equations on the right are the information about the three directions, T, N, and B, and also information about how they are changing as you move along the curve. And in this case, we're measuring two things. We're measuring how fast the curve is bending, the curvature, and then curvature happens really locally. You can think about curvature happening in a plane. And so then as you go from one point to another, that plane that you're bending on twists. And so you then get torsion. And so this is a lovely way of framing a curve. It's really useful in a lot of applications. But the problem is it's not good for what we want to do, because it has the curvature information, which will be fine. But then you've also got this torsion, and the torsion, we can't use that. So we can shift to a different way of framing the curve. And so now what we're going to do is actually just say, okay, I'm going to start with a frame, and I'm going to move that frame along my curve, and it's not allowed to twist around T, around the tangent. And so I'm going to have no torsion as I go around. And the nice thing that happens as we do this is that the surfaces we draw out from that system, those can be bent to lie flat. And so you're able now to create pieces that you can cut flat. They're called developable surfaces. And so now what we can do is take two of those flat cut pieces and attach them to each other to make a T shape. And basically what happens is that each shape can bend easily in one direction and is rigid in the other, but by putting them at 90 degrees, you sort of swap the easy to bend and the hard to bend. And so if you look at these things, the sort of, you have the surface, that broader thing, the sort of top of the T, and then if the spine, which is the shorter piece. The spine is giving the bending information to the surface by how it's curved, and the surface is giving the bending information to the spine. And so these two, what we can do is take our curve in three-dimensional space. You actually get two curvatures out of it, the curvature for the surface and the curvature for the spine. And those will, up to some additional, a little bit of additional information, basically define your curve. And so what we're doing here is sort of taking a curve in three-dimensional space, breaking it up into information about bending in two directions at right angles locally to give us two flat curves. And then we integrate together the curvatures of those flat curves to give us back the original curve in three-dimensional space. So what we can do is we can start with the form we want to make. We can turn that into two pieces we can cut flat. We can cut them flat on the plasma cutter. And then that integration happens in a jig, in a form, which holds the two pieces at right angles together. It's a paper model. And so here is one of the beams, and you can see here we have, this is the spine, and you can see the surface. And so the spine is bending alongside how the surface is curved, and then you can't quite see it as easily here, but the surface is getting bent by the curvature of the spine. And we can, because we can use this to make arbitrary curves, we can start to think about different shapes we can make. And so this is sort of the process of creating something that's a hyperboloid shape. So on the left, you see one way to do a hyperboloid. Then we can sort of modify the surface a little bit. So instead of having these sort of this grid of points, which is a little boring, we get this sort of nice double spiral with sort of thin spirals meeting this one spiral walkway. And so this is how the design that was used in that model you saw in the back of a truck. And this is again for Mathemalchemy. And here you can see the cut files for the different pieces. These then get glued together, and there you have the paper version. And I think one of the things that's sort of nice in this is you can also start to think about abstracting materials. And so I can test whether my things are working, because paper is one material that behaves well as a developable surface. Flat pieces of paper are very nice to use. And so I can test what I'm doing before I step up and do the same thing in metal. Now, whilst there's some abstraction you can do, again, the abstract, you have to have a conversation between the physical and the abstract. And as you can see here, that the metal needs to have a little bit more work and be treated in some different ways. The paper, in particular, metal basically creases very quickly as it folds. So with paper, it's really hard. You have to put a lot of effort to push it flat to make a crease where you start to stretch the fibers and change the way the paper is lined up. With metal, you have to do that a little bit more gently, one piece at a time, and you can see that sort of happening here. And some more, this is more pictures of the final piece. And here it is in the full Mathemalchemy exhibit. And the website. But the interesting thing, again, so at this stage, we had a system of building a bunch of developable surfaces and then being able to manufacture them quite efficiently with just using a, plasma cutter is an impressive looking tool, but it's also quite a widely available tool. Plasma cutting and welding is basically available anywhere in the world you have construction, whereas a lot of high-tech tools like CNCs are not necessarily available in those spaces. And so we were, we got experience working on these artworks of the system. At that stage, we had the control over the system that we needed to try to do things which were more in an engineering vein, where you can't just do something because that's the way it works. You have to you have a bunch of sort of external constraints, and you're a lot more rigid in what you might try. But here, this is the same system creating a form, and concrete is poured into this form, and you create a concrete beam. On the left, you see that beam being tested to see how strong it is. And the basic idea is I can take a box, sort of standard concrete beam as a box. And that's an inefficient use of material because it has too much strength in some places. And what I want to do is reduce the amount of concrete I use whilst keeping something as strong by moving around where the concrete is. And so that's where you can see the sort of form. And these metal beams that you look at in the frame, they're doing that same thing. They are basically creating this eye shape, which is going to give you a lot of strength with a lot less metal than a full box. And so by changing the shape, you can get a more efficient use of materials without actually affecting your strength. And so you can model that, but then this is actually building and showing that the models are fairly conservative. So this actually was able to take 120% of the weight that the model predicted it would be able to, which is sort of actually what you expect. If you model something and you say it can take a certain weight and it can only take exactly that weight, your model wasn't conservative enough, because obviously, if you're building something with concrete beams, you want to have a nice little buffer between where you say it's going to top out and where it actually causes damage. So yes, to finish, I want to talk about a couple of other projects I'm working on with this sort of manufacturing art mathematics, and the idea of bringing mathematical ideas into physical and working between abstraction and physical world. So here, this is one of two right now, but it's hopefully going to be a series of works. And this is a slice of a tree. So I take a photo of the slice, and I drew in every fifth grain line. And then I had an algorithm which starts at the central point, and then basically it draws lines out staying at right angles to the sort of family of curves. So basically, you can think about this, it's always going to be cutting at right angles to the grain as it heads out. And it keeps track of what paths it's already drawn. And as paths get further apart, after they get a certain distance apart, it adds in a new path. And so the whole surface is going to be covered in paths. And then there's one additional thing, as the paths start further out, they also start deeper. So here is in the middle of cutting what it looks like when it's sort of just done the first bit of cutting everywhere. Now, I did actually make a mistake with this piece. So bonus points, I'll give you a quick glimpse at this. If you can work out what the mistake is here, I guess bonus points in some meaningless metric. And here is one other fun project. This is going back to 3D printing and trying to work with 3D printing and create more interesting strategies of patterning on the surface of materials in such a way that you can have sort of free control for it. And this really, you start to really have to think about what the right abstract models are so that you can create these sort of more complicated toolpaths and control them. And so things like texture mapping is happening here. And there's also just a lot of discrete differential geometry. Right now, it's using a greedy algorithm to generate things, but hopefully a sort of more optimized thing will be written at some point. So that is my final slide. And so I will finish there. Thank you so much.
Thank you so much, Edmund. There is active conversation going on in, I think, all three of y'all's threads on the Discord channel. I suppose we did get an interesting question on the Q&A section that I figured I'd bounce, which I don't know exactly. Well, this is from Yanis Tsiligakis, who I'm sorry if I mispronounced your name, which asks, can we measure machines' mathematical imperfection? For example, how imperfect a machine-carved sphere from a mathematical sphere is. And I'm curious, if you have an answer to that.
I mean, so that is basically the heart of metal machining, understanding how to create precise cuts and the different forces and so on of a blade cutting metal. And with metal machining, if you really know what if you have some skill, you can get it accurate to thousandths of an inch. And if you really know what you're doing, you can start chasing another zero onto that. And so in that case, you're really thinking about not just the abstract model of the tool considers a lot more than just position. And so, basically it's sort of, you have to build a more sophisticated abstract model where you're thinking about how fast the tool is making, where the blades are going, the pressure, these sorts of questions are going to affect how much the tool deflects and thus exactly where you're cutting as opposed to where you're thinking of. I quite like wood because it's a forgiving material, and you really can't, it's hard to get in any way out of wood accuracy sort of beyond hundredths of an inch. And so the machine is capable without too much effort of doing that. The tool is never going to get, you're not going to notice the deflection of the tool if you're looking at those sorts of tolerances. So notions of tolerances and measurement. I mean, if there's a really wonderful video by Adam Savage where he's sort of exploring notions of how our idea of distance changes as we get smaller and smaller, and different, and how we go from measuring against a ruler to comparative measures where we're saying what is the difference between two things. So yeah, there's a huge amount there. On the other end, the clay, I really like working with the clay because it is so variable. And so you put in your perfect mathematical model for what you're doing, and then just sort of small changes in how the clay is pressurized and coming out give character, and you're working, the tolerances are now, very, very free, but that actually brings character to it. And you get sort of, these effects. Now, if you want to do things to really high precision, if you're sort of, like the metal machining, you need those high precisions at times because you're going to have two parts that need to fit together, and you need to be able to specify exactly the gap between those two parts, because if it's too small, they'll jam, and if it's too big, they'll wobble. So yeah, there's a lot you can think about with that. And you basically, as you need more precision, you pull more information into the abstract model and have to look at more advanced things. It all boils down to being multivariate calculus in the end, but different amounts of it.
Thank you. Well, I think it's after 1, so I would encourage us to migrate to the Discord to continue conversation. There are video channels there if folks want to hop in and chat, or when folks can also just hang out on the seminar channel and sort of.
Do we want to answer the other questions from the Q&A?
Oh, you're welcome to.
I think there's a couple of others. Some neurological differences between an artist that can carve the dodecahedron with their bare hands versus the artist that programs a robot machine to carve it for themselves. So I would say absolutely implementation in the technology. If you watch the machine carving something you drew, it's hugely beneficial to your spatial sense. On the other hand, making stuff by hand is an even richer experience from that point of view. And so there's definitely something to say, like make some stuff by hand. But the machines are high precision is more accessible in the machines than it is in hand making. There's a lot of stuff that the most skilled people can make by hand that I could make with a machine. But I think it's definitely, especially if you're watching the machine doing something you told it to do, that's hugely spatially really interesting to look at how people experience it. I've done things where artists have drawn a path, and then we've taken a photo of that and got the machine to draw that path, and you watch their hand move along the path that they just drew as the machine does it. So there's absolutely some and how we think about these tools in that sort of craft, engagement, and intuition sense. I think there's a lot of interesting space to go there. There's a question about drawing knots. I guess, is that drawing them in 2 dimensions or 3 dimensions? I think they are. I'm not sure, Michelle, exactly what you're asking there, but certainly there's lots of fun to be had with different knots and links. So I guess now we can go to Discord.
Okay, well, thank you all. So the Discord link is in the chat once again. If you haven't seen it, I'm including one more link to the Illustrating Math website, which you're welcome to visit. Thank you all again for coming. Thanks to the 3 presenters for lovely presentations once again, and hope to see you all next time.